My name's Claudio, and together with Michele, we're going to give you an overview of Work Package 1, Predictive Design. This is a work package that involves all three universities. The academic lead, Douglas Kell, is out of Liverpool, and there are members from Manchester and Sheffield, and of course AkzoNobel involved too. The aim of Work Package 1, and Simon talked about it earlier, is to make deep links between the individual components that comprise fully formulated coatings and correlate them with a description of performance by use of machine learning. And this diagram here is a sort of diagram to represent typical product development. And you start with some targets, and then you formulate a coating, and then you do some testing. And if you're lucky, you have a product, but more often than not, it's not right, and you have to go and reformulate and do more testing, etc., etc. It starts with formulation, the challenge. And what do we mean by formulation? I mean, coating recipes typically contain 10, 20 ingredients. Again, Simon highlighted some of those ingredients, and every ingredient can have a significant impact on the properties and corrosion protection. It's a formulation, it's paint, but a good analogy, and it's been used in lectures by Stuart and originally by Professor Scantlebury, is cake. And there's actually a surprising amount of correlation between cake and paint. Both made according to a recipe with its specific ingredients. Each ingredient has an important part impacting the product, and how you make it is also important. And every ingredient can have a significant impact. In cake, if you're making a fruit cake, a spicy fruit cake, you might use a little bit of cinnamon. If you leave out the cinnamon, it misses some of the attributes you're after. But you can also put too much cinnamon in and absolutely overpower it. And what we have here is an example of, in paint, of changing just one ingredient can go from good performance to bad performance. And I didn't press that. As with all these things, when you have a combination of ingredients, the more ingredients you have, it goes up exponentially. Typically 10 to 20. If you take 10 of those and you want to vary them at 2 different levels, you're at 1,000 different formulation combinations. If you want to do 20, you're up at 1,000,000 at 2 different levels. So you're quickly ending up with a formulation space that's enormous, and traditionally you narrow it down. And because exploring that full formulation space is very, very time consuming.
So in the same way as we have challenges in terms of formulation, we also have challenges when it comes to the corrosion testing. So if you take, for example, a car that gets produced, and most of the part of the car will have some sort of protective coating to ensure their durability. Once the car is sold, that it enters the market, it will experience a large variety of environmental conditions. And each individual car will experience a slightly different environmental condition. So when you develop a protective treatment, you need to have some sort of testing that is able to provide some confidence that the car will be able to last for the expected lifetime. And that is not easy because the variety of environment makes the condition to be tested quite variable. So ideally, you would like to have some sort of test that is able to accelerate the various degradation mechanisms that the car will experience, but not substantially alter the way the failure occurs. So what we have available in practice to test the corrosion resistance of some protective solution are essentially 3 types of testing. The first one is natural exposure or field type test. In this case, effectively, the part is painted, or this protective treatment is applied and is exposed to an outdoor environment, which is considered particularly aggressive. So that test has some strong similarity with at least some of the service condition, but at the same time, it takes an extremely long time. Alternatively, we have laboratory testing, and this can be split in 2 major categories. One are sort of cabinet type testing, where we deliberately produce an artificial environment that we believe that accelerates some of the degradation processes, and we subject some specimen to this artificial environment and observe how they behave after a set time. This test is relatively faster compared to the natural exposure, but the arbitrarity of the environment to some extent limit the correlation with what may be the actual performance. The final type of tests are more academic type of tests. They are electrochemical, and they effectively rely on the fact that corrosion is an electrochemical process where electrons are exchanged between the various areas of the metal. So if we apply an electrical signal in the form of current or voltage, we can measure a response, and this response contains information about the corrosion processes. So what are we doing in work package 1 in terms of corrosion testing is try to act on this part of the development cycle that Claudio was outlining at the beginning, and essentially improve the laboratory testing methods, such as when we send some candidate system to field testing or to longer term testing, we have a high confidence that it will be able to perform as we expect. So by doing, in order to do that, we try to exploit the testing methodologies that we have and integrate them with artificial intelligence, such as the process can be automated and we can obtain better results, better information to feed back to the formulation. But what is machine learning? Machine learning is something that we can understand if we look at this example problem. So imagine that you have to identify all the bananas in this image. You can see that you know they appear quite differently. Some of them are in black and white, some of them are yellow, but the yellow is not too difficult from the yellow of a lemon. You could rely on the shape, but again, they might be similar shape that are difficult to distinguish. So the traditional approach, the traditional coding approach, would essentially rely on a human being having a very good understanding of what a banana is, then writing a set of hard instructions, then a computer would execute in order to be able to recognize a banana. So that could be, for example, the color, the shape, or other features that the human being has interpreted as discriminating for a banana. The machine learning approach is different. It relies on the fact that we feed to the computer a large amount of data, or banana and non-bananas image, with description of whether or not they are a banana, and then the computer itself uses a machine learning algorithm to learn how to discriminate a banana from a non-banana. As we increase the number of data and as we increase the time, the computer can learn better and become more efficient in discriminating the banana from the non-banana.
So how do we apply this to formulation? Well, again, typically in development, you have a formulation space, which is this whole box, and there's time. And you start by looking at a number of different avenues, what you think might work to achieve your target. But sooner rather than later, at some point, it starts focusing down an avenue, and you end up with, exploring a limited set of ingredients. And you might well end up with your paint or cake that you want. And that's good enough, but is it the best one, or is it necessarily the best one, or can you do better? And this is where machine learning, comes in and can help us. It can help by taking by taking the data you have and exploring around the space that you have. Now, machine learning, people use the landscape metaphor, where obviously you want to get from where you are up to the top of the mountain, assuming that the top of the mountain is the goal. And it helps explore the various different routes, and the routes have, other peaks, other valleys. And what it doesn't want you to do is, what you don't want to do is spend a lot of time in a valley when your target is to get to the top of the mountain. So the machine learning helps you navigate this space intelligently, but it's all based on the data that you have. And so what we've been doing in work package 1 is obviously using machine learning to find other optimums. It's a data-driven process. It's different from hypothesis-driven. It takes the data and it comes up with what it believes are going to be good ones, and then you can develop hypotheses around it. So what I've done in the work package is feed in a lot of historical data, and we've found a data set where we've been able to, around one area, so it's around this type of problem, where we have looked at a number of different starting points, and we have ended up in an area, and we're looking to see what machine learning can tell us about new combinations, different combinations that can give us, different paints, different cakes with different properties that still meet the targets, or indeed might have different properties, which enable us to exploit them in other ways. So it's exploring that space. Yeah, it can also assess parameters with the biggest impacts and give you an idea of what having something in will be really beneficial, or not having something in will be beneficial or not. And it can predict new combinations. And the first predictions have been done, and we're in the process of validating it.
So in terms of corrosion testing, if you look at the problem of recognizing and quantifying corrosion, it's not too different from the problem of recognizing bananas from other fruit. So to a trained eye, it is quite evident in which of these cases corrosion is more preponderant, or in which of the curve there is a clear evidence of a corrosion attack. So what are we trying to do in work package 1 in terms of corrosion testing is to combine the cabinet type testing that provide information on the practical performance of the coating and electrochemical testing, such as we can train a machine learning algorithm to interpret the data and to quantify the level of corrosion, such as once we have the trained machine learning algorithm, we can use it to automatically interpret corrosion data and therefore increase the number of tests that we can do, and therefore increasing the amount of information that we can obtain. So in practice, what we are focusing now is to work on electrochemical impedance spectroscopy data that essentially contain information on, for example, the rate of corrosion, the thickness of the coating, the amount of water that has been that has entered the coating, and try to develop a machine learning algorithm that can automatically interpret this type of data. So this is an example of the sort of things that we can achieve. Essentially, in this situation, we have that when the red line that represents the fitting from the computer overlaps with the black experimental point, that is an indication that the machine learning algorithm has been able to extract the essential information on the corroding system. So in this particular study, we have been evaluating the number of examples that we needed to provide to the machine learning in order to train it effectively. And as you can see, we have demonstrated that the quality of the training becomes fairly good if we use about 200 examples. Another thing that we are trying to do is to train a machine learning algorithm to recognize specimens that behave well when exposed to an aggressive environment compared to specimens that behave less well when exposed to a corrosive environment. So in this case, I am showing an example where we have two types of specimen. The green one are better than the red one. And these two types of specimen produce impedance spectra that are significantly different. So we have been able to train the machine learning to recognize the spectra generated by group A sample from the spectra generated by group B sample with relatively good accuracy, and therefore to automatically identify which specimen corrode more and which specimen corrode less.
Okay, I'll just finish off with the next steps and impacts. Work package 1, like I said, we have got to the stage of predicting some formulations, so we'll test them, make them test them, feed it back into the machine learning model to let it to improve the models. We're in the process of collating more data from another data set, and say well on the way with the corrosion testing network. And the impacts, we're looking for it to improve our predicted qualities, knowing how we can use machine learning with our existing data sets, and more importantly, how we use it better, going forwards. No, I didn't touch anything. How we go forwards, and designing better, faster predictive tests, and interpreting electrochemical measurements by machine learning. But ultimately, it all comes down to if it's a useful methodology, it will accelerate our new product development. Thank you for your attention.